got to see during the total eclipse in 2017. See how there's that glow around the sun? That's energy leaving the sun, and it happens all the time.
And while there's always outflow from the sun, there are particular moments where the sun has an outburst.
And that gets called a solar flare, which is what Dan studies. Dan's a scientist at NASA. These studies had a better forecast these big bursts of energy. See, solar flares, they have the potential to affect us on Earth.
And it can disrupt radio communication for airplanes. It can cause GPS inaccuracies. So there's actually a lot of effects we feel through our technological systems, and we have to be prepared for them.
So why haven't we heard about this before?
For the last few years, and the sun's been pretty quiet. We haven't seen a lot of big outbursts.
But all that is about to change. NASA has just discovered that the sun is entering a new phase. A phase where the sun will have a lot more of these solar flares than usual.
Going forward the next couple of years towards like 2024, 2025, these events are going to be a lot more common.
What if one of these big energy bursts is way, way bigger than usual?
That actually can damage wide-scale power grids and cause huge blackouts.
On July 19th, 2012, the Solar Dynamics Observatory captured this incredible footage of the sun. This clip was recorded with one frame every 12 seconds, meaning every second of this video represents 6 minutes of real time. This event began with an intense solar flare, a sudden release of magnetic energy sending ungodly amounts of energy in the form of radiation and light into space. This particular solar flare was followed by a coronal mass ejection, a massive twisted bubble-shaped eruption firing a colossal cloud of electrically charged particles into space, which can disrupt interplanetary magnetic fields and interact with Earth's magnetic field in what is known as a geomagnetic storm. Finally, as the solar storm subsided and the eruption bubble began to cool, we were treated to one of the most mesmerizing events in our solar system, coronal rain, where the remaining charged plasma cools and falls back to the surface of the sun, forming these beautiful cage-like structures as the particles follow the sun's magnetic field lines back down. An astoundingly beautiful event, but had it happened just a week earlier, the flare would have been pointing squarely at Earth, and it wouldn't have been the first time a solar storm affected life negatively on Earth. In 1859, a similarly powerful solar flare called the Carrington event did hit Earth, treating people as far south as the Caribbean to the Northern Lights, while also knocking out major telegraph systems in both Europe and North America. In some cases, the geomagnetic disturbances were so strong that they sparked fires, shocked telegraph operators, and even allowed the telegraph system to work with no power. In 1989, a large geomagnetic storm caused a blackout in Quebec after the coronal mass ejection managed to trip circuit breakers in their grid, leaving 6 million people without power for 9 hours. So clearly, these storms have the power to really mess with vital technologies that keep our society moving. But how exactly do they do it? To understand this, we first need to understand some basics of how electricity is generated in our power stations. As you probably know already, we generate electricity by moving a wire through a magnetic field, or vice versa. The basic law behind this is called Faraday's law, which states that any change to a magnetic field surrounding a coil of wire will cause an electromotive force to be produced, otherwise known as a voltage. The voltage can be considered the force pushing the electrons through a wire. If they are free to move, a current will be produced. The current is a measure of the rate of flow of electrons. We generally generate electricity by rotating a coil of wire inside a magnetic field. We do it this way simply because rotational motion is efficient with no changing of direction, like linear motion forcing us to decelerate and lose inertia. But we can generate currents other ways, like dropping a magnet through a coil of wire. This moves the magnetic field itself rather than the coil of wire. So, stationary wires can generate currents when a magnetic field changes around them, and our electricity grid happens to be made up of millions of kilometers of stationary wire. We have effectively turned the planet into a massive electric generator by surrounding the Earth's magnetic core with all this conductive wire. The only thing that's missing is a large shift in the Earth's magnetic field. Unfortunately for us, that is exactly what coronal mass ejections do to Earth's magnetic field. On March 10th, 1989, the sun blasted a cloud of charged particles so large that it dwarfed our planet in size. It raced through space at 450 kilometers per second before crashing into the Earth's magnetopause, the boundary between Earth's magnetosphere and interplanetary space, sitting about 65,000 kilometers above Earth. It struck with such force that it literally shook and trembled our planet's protective magnetic field. The first phase of this is called the sudden storm commencement, where the coronal mass ejection first arrives at our magnetopause, causing the magnetosphere to compress on the daylight side of the Earth, resulting in a sudden increase in the intensity of the geomagnetic field in that region. The next phase results in a decrease in intensity as an electric current induced in the magnetosphere and ionosphere pushes the boundary of the magnetosphere outwards and results in a decrease in the geomagnetic field. And the geomagnetic field can continue to vary from hours to days after this initial burst. So, these geomagnetic storms cause shifts in the Earth's magnetic field, which drives induced electric currents in anything capable of carrying them. That can be the ground, ocean, or our electricity grid. If those currents enter our grid, they can wreak havoc on essential infrastructure. So, it seems like a disaster is waiting to happen. What are we doing to prepare for the worst? Unsurprisingly, one of the largest industries on Earth has thought pretty hard about this problem and has set out guidelines on how to deal with such an event. As mentioned in my recent solar sailing video, we currently have several satellites parked in Lagrange Point 1, a point between the Sun and the Earth where a satellite can maintain a constant position, and thus allow us to receive advanced warning of any coronal mass ejection. This point confused many commenters who assumed solar flares were simply bursts of radiation travelling at the speed of light, and thus no speed of light communication method could give us advance warning. But these eruptions of particles travel at a fraction of the speed of light, about 0.15% the speed of light for our above 1989 event, and thus can provide up to an hour of warning time. We also have some less definitive warning signs that the Sun may point a coronal mass ejection in our direction by observing sunspots, which are dips in brightness on the surface of the Sun, which occur as magnetic energy bottles up in the solar atmosphere before being suddenly released. These sunspots come in cycles of low and high activity every 11 years. This warning time can provide grid operators a little time to prepare for any anomalies, but they are more useful for GPS satellites whose accuracy is affected by ionosphere disturbances as their radio waves refract through it, and thus need to adjust their signal to compensate for it. In severe solar storms, these warnings would give industries where GPS malfunction could lead to loss of life, like airliners, vital time to prepare. To protect our grid, it's really a matter of designing it in a way to be able to deal with these induced currents. Let's take a deeper look into that 1989 blackout to see what really happened and see how grid operators can prepare. The first malfunction occurred as a result of transformers becoming saturated. Power transformers are placed at intervals between high voltage transmission lines and power generators or local distribution lines to step up or step down voltages. So what does saturation mean? Transformers work by winding wire from the source around a ferromagnetic core. This generates a magnetic field inside the core, which can in turn induce an electric current in our secondary winding. If our primary wire has more windings than the secondary wire, it will step down the voltage. And if the secondary wire has more windings than the primary wire, it will step up the voltage. These transformers form an essential part of our grid, but when the core becomes saturated, it interferes with their operation. Saturation just means that the magnetic core has reached its maximum magnetic flux capabilities, so an increase in current and voltage will not result in a subsequent increase of magnetic flux. If this happens, the voltage induced in the secondary winding can no longer match the waveform as the voltage powering the primary coil, so the waveform of the secondary wire becomes distorted. When this happened in Quebec, the grid voltage became unstable, causing the protective relays to disconnect 5 high-voltage transmission lines, including one from a hydroelectric facility. As the hydroelectric facility was disconnected, it experienced a rapid loss of load, meaning its power had nowhere to go, which caused the voltage to suddenly increase, which damaged 2 step-up transformers as a result of excessive heating. Saturated transformers are the root cause of most grid malfunctions during magnetic storms. However, in 1989, the knock-on effect of these waveform distortions is what caused the majority of the damage, as electromechanical protective relays tripped and cut off sections of the grid. Electromechanical relays are essentially switches that turn on and off when electric current flows in the control circuit, creating a magnetic field in an electromagnet and pulls an armature down to complete a circuit in a secondary circuit. These can be combined to form logic gates that are more complicated but are in general not programmable to deal with anomalies like distorted waveforms caused by transformer saturation. Today, we have much smarter microprocessor technology that can be programmed to deal with these issues better and maintain grid stability, but because of the electromechanical relay's reliability and long service life, there are still thousands of these older devices in the grid infrastructure, but they are slowly being phased out for more modern technology, especially in northern and southern regions more susceptible to geomagnetically induced currents. We can also block geomagnetically induced currents because they are direct currents, where our normal power is alternating current. Capacitors can only transmit alternating current because capacitors don't physically complete circuits. They are just large stores of positive and negative potentials that switch every time the current flips. DC currents don't flip, and thus capacitors do not allow DC currents to flow. So, we do have options to minimize the effects of these disturbances.